master students. The first master student is Muhammad Hijazi, and the second one is Abdul Rahman Abu Qamar. So we are going to start with Muhammad Hijazi, whose presentation is going to be about improving the performance of OFDM with subcarrier power modulation using signal space diversity technique. So welcome everybody, and thank you for joining us, and you can start the presentation, Muhammad.
Okay, thank you very much, Doctor. Hello, everybody. My name is Muhammad Hijazi. Today, I want to speak about my thesis. It's about signal space diversity for improving the reliability performance of OFDM with subcarrier power modulation. This is the outline in my thesis. About signal space diversity, and I will talk about maximal ratio, my result, what are my results, and also what I have concluded. First of all, we know that there is a demand for high data rates worldwide as a result of the new application and the needs of people. Consequently, researchers and engineers are always trying to introduce novel techniques for improving spectral efficiency, and this will be associated with additional errors. So also the techniques must reduce the bit error rate in receiving data. So, my friends, this is the challenge. The challenge is to design and build a system model that can improve the bit error rate performance for ready OFDM-SPM conventional design, which have been made to increase the spectral efficiency comparing to the normal OFDM. Nonetheless, it has a defect that bit error rate has a poor improvement. So, first of all, or secondly, I want to talk about what is OFDM-SPM. It is a model that aims to send more bits per subcarrier by using the power of the subcarriers itself, regardless the normal bits that conventional OFDM transmitted. Here in this figure, we know that in QPSK modulation in the normal OFDM, when we change the in phase modulation, we make a transmission for 1 bit. So every subcarrier can transmit 1 bit per simple. But in OFDM-SPM, we also use the power of the subcarrier. So, to give an example, let us display a case here. Both conventional OFDM and OFDM-SPM can be used, assuming 104 bits were required to be transmitted. Conventional OFDM with QPSK, since it carries only 1 bit per subcarrier, we would require a total of 104 subcarriers, each requiring bandwidth and power. As such, the total resources using by conventional OFDM would be 104 and 104 bandwidth in terms of bandwidth and power. So, on the other hand, OFDM-SPM that will use the power of the subcarrier would require only 52 subcarriers, as each subcarrier carries 2 bits, resulting in a total results usage of 52 bits in the bandwidth. So in other words, OFDM-SPM reduces the total power usage by a half as a consequence of using only half the number of the subcarriers used by conventional OFDM. This is a figure that shows OFDM QPSK SPM. Here we see the original QPSK points And we see also the QPSK SPM points. But as I said before, there is a small problem that OFDM-SPM has a poor bit error rate performance. So my contribution is to increase the bit error rate performance and the throughput for this conventional design by using SSD. We will go to the SSD. It is a technique that improves the performance over feeding channels since there is no need for using extra bandwidth or extra. So how SSD work? First, we know that in the constellation point for QPSK, for example, we have 4 points. Every point is holding 2 bits, one from in-phase components and the other from the quarter component. So the first step in signal space diversity is to make the rotation. We make a rotation for this constellation. I mean, in phase and quarter component for the simple or the subcarrier. And this ensures that no two simples in the signal constellation has identical in phase and quarter, as this will make interference intersimple and increase the potential of the bit error rate. So our goal is to maximize the minimum product distance of the rotated constellations. You can see in this figure, this is a constellation rotation. Here we see that we make a rotation for the points. When the rotation about theta equal to 0, we see that xi, which is the in phase, equal to ai, and yi equal to bi. But in the case of rotation, we will see that xi will change. It's equal to ai cosine theta minus bi cosine theta. And also for the quarter component, yi will equal ai sine theta plus bi cosine theta. So just like I said before, here in this figure, you will see that the minimum product distance of the rotated constellation here is more in the case of the rotated constellation. So after the second step, after make a rotation, we will make interleaving. And this is the second step in the signal space diversity. Transmitting in-phase and quarter components coordinates of the transmitted symbol over distinct sub-channels. So in order to destroy the correlation between them, which will make I and Q channels independent. Therefore, the received data can be recovered even though one of the components suffers from deep fading. So in other words, we make a delay to the quarter component in the subcarrier. So in interleave, and the imaginary part will bypass and the real part is interleaved in order to avoid the worst channel condition where both parts experience deep fading simultaneously. This is when we make a rotation, then make interleaver to make the signal space diversity. So this is an example for signal space diversity. This is just like I said before, with the rotation angle equal to 0. In the case of coordinate interleaving, there is an improvement in the bit error rate. Sorry, right now there is no improvement because the rotation angle is 0 in the both cases, coordinate interleaving and no coordinate interleaving. But when we make a rotation angle for 15 degree, for example, here there is an improvement in the bit error rate in the case of the coordinate interleaving, but with no change at the case of no coordinate interleaving. And this is the rotation angle for 30 degree. You will see, my friends, that there's also better improvements. Okay, this is the system model that I have used. Here we can see the incoming bits, which are ones and zero. After converting them from serial to parallel, half of the incoming bits will go to the normal modulation, for example, QPSK, and the other half will go to the power subcarrier allocator, as we consider high amplitude as 1 and low amplitudes as 0. But in our system, I made a rotation for the constellation point to apply the first step in the signal space diversity. After this, the power allocator bypass and the rotation constellation point in the active subcarriers will go to the coordinate interleaver to delay the quarture component. The real part in the subcarrier, for example, one subcarrier will hold one real part from the first constellation point and the one imaginary part from constellation point. We will perform including IFFT in order to convert it from time domain to frequency domain, then adding cycle prefix as usual to remove subcarrier interference and perform a digital to analog conversion, then to the antenna to receive it by the receiver. Here, the receiver system model, that the signals that are coming from the transmitter will have many problems due to the fading channels that carries it due to multipath channel. In other words, it's Rayleigh fading effects and the normal additive white Gaussian noise. So we made our design more effective. After receiving signal from receiver antenna, the analog to digital converter converts signal from analog to digital, and then cycle prefix will removed and go to the FFT to return back from frequency domain to time domain. After this, the OFDM in time domain will go to the de-interleave, so every subcarrier have its original components, in quarture and in phase and quarture components. Then the bits transmit by power subcarriers, allocator recover, and other constellation points who was modulated by QPSK will be derotated so that all incoming bits were received after this, converted from parallel to serial, and having our data received to the original. I want also to speak about maximum ratio combining. In telecommunications, maximum ratio combining is a method of diversity combining in which the signals from each channel are added together. So, as in MRC, I used two antennas to receive the same signals from two channels and combine these signals using the weights. For maximum, we still co-phase the signals. Then we weight the signals according to their SNR. The rationale is that some channels are more reliable than others. So we should listen to their signal more than others. For example, just like if you hear something from multiple individuals, you probably will not weight each person equally because you know who is more reliable compared to the others. So this is the design for the maximal ratio combining. The transmitting design is the same in OFDM-SPM. We only make amendment in the receiver design. So what about the results? Before speaking about results, I want to talk about what we mean by using power relocations or power policy in the OFDM-SPM. So low and high denote the low and high power levels of the subcarrier, whereas EB denotes the energy per bit. In the case of the power reassignment non-optimized mode, the safety is reassignment to the high power subcarrier, while the lower power subcarriers are set to unity. So this is the first result that I have made from the MATLAB. As you see, my friends, we note that when we use signal space diversity to the conventional OFDM-SPM, we achieve or save 18 dB in the SNR. For example, the bit error rate at 10 dB in the normal OFDM-SPM is 10 to minus 1. But in our case, when we use signal space diversity, we will get 10 to minus 2 bit error rate. And that's considered a significant improvement. And regards the throughput, we got the same throughput after 10 dB. Here, after 10 dB, we got the same throughput, but we also have better throughput from 0 to 10 dB. Okay, and now we will go to the case of the power safe modes. Just like I said, optimized power policy. There are poor performance for bit error rate for OFDM-SPM comparing to the normal OFDM. But on the contrary, with signal space diversity, the performance increase and better than also the normal OFDM. And this is also the throughput. Now, let us compare the bit error rate between OFDM-SPM and also when I use MRC and when I use the signal space diversity. Here, from the figure, we got it from the simulation. You will see that MRC does a small improvement for bit error rate comparing to OFDM, and also with the cost of the complete in the MRC. We know this is disadvantages in the MRC that it has a small complexity in the design. But at the end of the day, signal space diversity proves that it made better results. Here, from the figure, the curve in yellow color that is related to the average OFDM-SPM using signal space diversity, and the non-continuous blue color that's related to the average OFDM-SPM using MRC. You will see that to achieve 10 to minus 2 here, bit error rate, we need 22 dB in the signal to noise. But at the case of using SSD, we need only around 11 dB to get the same bit error rate. So, and this is also a comparison between the throughputs for using MRC and using signal space diversity, and the results show that the better throughput is for signal space diversity comparing to the MRC. So what we conclude? We conclude that when we apply signal space diversity to OFDM-SPM, for example, QPSK modulation, the effect of the oscillating rotation is only marginal, and the improvement in the bit error rate is mainly due to the interleaving. And also, OFDM-SPM using signal space diversity provides a considerable improvement in the bit error rate and throughput over the traditional OFDM-SPM and OFDM-SPM using maximum ratio combining. And this is, my friends, the reference that I have used. And thank you for my supervisor, Dr. Jihad. And thank you for your attentions. And if you have any questions, I will happy to answer it. Thank you very much.
So thank you, Hijazi, for the presentation. I think we have a couple of questions. Maybe this is, first of all, Dr. Shahram can ask you some questions so that you can improve your work more. And
Okay.
then we can move to the students to ask you some questions as well. So, Dr. Shahram.
Thank you, Mohammed, for your presentation.
Thank you very much.
Actually, this is not my domain expertise, but I find out your presentation very useful and it is complete. So actually, I don't have any further question. So thank you again for your good presentation.
Thank you very much. Thank you very much.
So, from the attendees, so anybody has any questions about this scheme called OFDM-SPM and how he integrates it with signal space diversity? So if you have any question, you can also write in the chat. If you don't have any question, we can move on to the next presentation as well. So since there are no questions, let's see if there is any question here in the chat. There are no questions. So I think we can start the second presentation. So could you please share your screen, Abdul Rahman?
Yes, Professor, I will share it.
Okay, thank you.
Can you see my screen now? Can you hear me, Professor?
Yes, we can see your screen.
Okay, hello and welcome everybody to my presentation. My name is Abdul Rahman Abu Qamar.